Hello everyone, welcome to my first video of the reinforcement learning series. Today we would cover some basics of reinforcement learning as well as would learn about one of the most basic algorithms in RL called policy iteration. But I guess most importantly, we try to solve a simple problem called small grid world using that algorithm. This all started, when I started revising RL. I had studied RL 2 years back as part of my MTech coursework at IIT Hyderabad. But when I was trying to revise right now, I realized there is no uh, good videos or illustration of this classic grid world problem from the Sutton and Barto book. So I thought, okay, why not just make one myself? So let me share my screen and show you the actual problem statement. Then we can dive into the theory. All right. So yeah, this is the grid world, 4 by 4, and the rules are simple. There is a reward of -1 for every transition, and so the goal would be whatever state you are in currently, you are ideally supposed to reach any of the two terminal states which are in gray, with minimum number of steps, right? And now here they have mentioned that it's like um, there is equal probability of going up, down, left, or right. However, say suppose you are in eight this state already, right? It's already and if you take action which is go left, since there is no left in this grid, right? It will just stay wherever it is. Now, I hope the this problem sounds simple enough. So to solve this, we'll use an algorithm called policy iteration. This is the algorithm. I mean, it looks scary, but as we break it down and also solve it by hand, it will become simpler. So let's just try to understand these notation first, right? Yeah. So maybe even before diving into the notation, firstly, let's try to think, right? What differentiates RL from supervised or unsupervised learning? In supervised learning, we're given the target labels, right? Be it the continuous value for regression or a class level for classification. And whereas in unsupervised learning, there are no labels. We just have to find out from the data. And in contrast to these two popular ML methods, right? How does RL work? Firstly, the goal of RL is to find the optimal policy, either directly or indirectly. And we'll talk about it in a moment. So we got to find the optimal policy, and we have to learn it via interaction with the environment, right? From the rewards that we get. So there are different, cases or scenarios here. Firstly, there could be a case where, we know all the rules. For example, going back to this mm, grid world problem. So firstly, we know that uh, the reward is always -1, right? For every transition you make. And secondly, it's we know that it's equiprobable uniform random. For example, if I'm at the 5 cell, I know the probability of going up, down, left, or right is all equal 1 by 4. So I know the entire system dynamics. In such cases, we can use any of the planning or dynamic programming algorithms like policy iteration. There would be cases when we don't know these rules, the transition probabilities and the reward functions. Then we'll have to just take some actions and see what rewards we get and learn from that. But that's the topic for another day. And right uh, now, so if we right look at the algorithm itself, policy iteration. So it has like three states. Firstly, we initialize the value for each state randomly. Now, what is a value function? For that, let's first understand the what is called a return. Return is the a sum of all the rewards we can get from a given trajectory, right? For example, suppose I am at a cell 6 in the grid world, then I take 5 steps to reach the terminal state, right? Then I'm getting -1 reward at each state, so the return would be -5. Now, that being the return, that is sum of rewards, now we need to figure out how good a state is, right, before we can formulate a policy. Now, why is that? Because so there are again there are two ways to look at reinforcement learning. One is value based, and another is policy based. So what we are studying today, it's a value based reinforcement learning, as in firstly we'll try to assign a value to each state, like how good is that state, right? And once we say somehow are able to evaluate the right value function, which we'll see in a moment, right? All we got to do is say, greedily take a step, as in, suppose we are at -18, right? So there are like four options to go from here. I could go left, which gives me -14, up -14, right -20, and bottom -20. So what is the best course of action that will give me maximum reward? I could go either left or up, right? So that is the greedy policy. So in this current scenario of policy iteration, this is one of the examples of value based RL. So we'll first have to evaluate the value, and then be greedy with respect to that, as in, take an action that maximizes the value. And what is this value? This is nothing but the uh, average of the different uh, mm, it's the average of the returns from all the different trajectories that I can take from my current state. For example, if I just go back to this grid world, right? Initially, we are at random policy, right? Suppose I am at 5. I could go either way, right? Up, down, left, right. And based on what action I take, it will lead me to a different trajectory. So, and each of these trajectory will have a different return or sum of rewards, right? If I just average them out, that would give me the value of 5. So, mm, that's the value function. Similarly, I can get a that was a state value function. Similarly, I can get a action value function as well, as in I'm at state 5 and I take a left action. What is the value of that action? How good is that? That is again the average of all the mm, returns from all the possible trajectories at that point, right? Now, let's just, yeah, we'll use this definition of value function and just substitute this gt as in return in the below equation. One thing to note is that the return here, it could be discounted or undiscounted, as in sometimes what we do is we place lesser importance to the future returns. Probably the concept is like this: 1,000 rupees that I get today is more valuable than the 1,000 rupees I'll get 1 year later. The return GT could be the discounted sum of all these rewards, but in our grid world problem, the gamma is 1. There is no discount, so you can just ignore this. So for our case, return is just the sum of rewards. And what is value again? Just to jog your memory, it's the average of all the returns from all possible trajectories starting at that status, right? Now, yeah, let's just use that definition of the value function and then substitute the GT, right, which is sum of discounted rewards. So we now do some very simple algebra, as in we take out the first term RT plus 1, and then from rest of the terms we take a gamma common, right? This leads and then we use the definition of expectation of function of a random variable, which is like, say expectation of g of x is nothing but summation over all x, and then g of x into probability of x, right? So we use this property to get finally this equation. Now let's try to understand this, right? So what it shows is that the value of a state S, right? What it is, how do we determine this? We first see what are the possible actions A we can take from this state, right? And once we have taken that action, right, depending on whether the system is deterministic, whether the environment is deterministic or stochastic, the same action could lead to either the same reward, same state every time, or different states. For example, in our grid world, say if we are in state 5, right? And then we take action left. So now we can say with 100% certainty, yes, we'll go to state 4, right? So this is a deterministic environment, but it might not be in every case. So yeah, now going back. So once we have taken an action, we first check what could be the given that state. In that state, we have taken that action. What are the possible next steps? That is S apostrophe, right? And that for and what are their respective probability of occurring. For example, in our case, well, when we take a left from 5, right, with 100% probability for the state 4 will happen, so we have only one state as a resultant. But anyways, what are the states, what are their possible probabilities of happening, multiplied by what reward will I get when I go to that state S bar, right? And plus the discount into that the current estimated value of that state S bar, right? This is the Bellman equation. I know it probably looks a bit complicated right now, but once we solve it by hand, it will become much simpler. So just to give a maybe express it in a simplified manner, what we're doing is like a bootstrapping. Like we are at a state S, right? And we want to estimate the value of state S based on all the possible future states S apostrophe, right? So yeah, now this is Bellman equation, and we'll use this for policy evaluation step of our policy iteration. Now let's just go and have a look at the entire algorithm, right? So firstly, what do we do? For all states, we just randomly mm, uh, initialize a policy, right? A random policy, and then what we do for we do a step of policy evaluation, which is using the Bellman equation. Now what happens that that equation we could solve directly analytically, but then if the number of states is too high, it becomes computationally very expensive. So we can even do it iteratively, as in start with a random value, say v naught for each state. Only thing we have to be careful is that the terminal state has to be 0. Rest of them can be anything, right? So we start the random value and then we just keep iterating multiple cycles till there is a convergence. As in, the policy is no longer improving. And what is policy no longer improving? If you just recall, some time back we discussed that policy, the greedy policy that we can obtain is nothing but the argmax at that particular situation, right? So we don't have to wait till my as I iterate through this policy evaluation, right? I don't have to wait till the value function is exact, like 4.9, that is the optimal value function. I don't have to wait till that. I just have to wait till the my policy, right? That is argmax directions are not changing anymore. So anyway, that is policy evaluation. Now going back to the algorithm. Yeah, so once there is a convergence in policy evaluation, what we do is we now do a policy improvement state, as in we take an argmax, right? So for each state, so we try to find out which is the step I should take to maximize my rewards. Now, since the policy evaluation itself, right, it wasn't the uh, since it wasn't the optimal policy pi star yet, so we have to keep repeating it till the action I choose at policy improvement stage is same as the the action recommended by the policy. So you have to repeat it multiple times. Now, for today, we'll just go through the policy evaluation state with the small grid world example. Now let's just have a final look before we jump into actually solving it. So, uh, right, let's, sorry, the small grid world. Right. Uh, so just to jog your memories, there is a -1 reward for every action, and the agent is uniformly random. We can take any of the four actions up, down, left, right uniformly. But if there is a impossible action that takes, as in there's something that takes us off the grid, it will just remain there. So for example, if we are uh, at yeah uh, and so here are some of the examples. So if we are at 6 and we take an action right, with 100% probability we'll land at position 5. And so suppose we are at 7 and there we take right, but there is nothing to the right of 7, so it will just remain at 7. So we have 7 given 7 comma action right is 1. So let's try to solve it by hand, that is by Excel. So just to summarize, there is a policy evaluation step which we do iteratively, and then there is a policy improvement, right, where we are greedy with respect to the current policy. Then we get a new policy, then we do the policy evaluation with respect to the new policy, right, and so on and so forth till convergence. But here we'll just do the uh, policy evaluation for the first iteration of policy iteration, right? So I have just pasted the formula here, and so the gamma is 1, there is no discount, right? So now let's try to evaluate for this state which we are denoting as state 1, right? Because this terminal states are already 0, we know, and we have initialized everything as 0. So now, since we are at state 1, we could take again four actions, right? And we are already told that four actions have equal probability of 0.25 or 1 by 4. Now what would be the reward? We have been told that reward is always -1. So let's just go ahead and put them here, right? And I suppose I am at this state 1 and I take action left. Where did I go? I'd go here. And what is the reward here? 0. And so if I go to right again, I get a 0. And what happens if I take action up? I'll remain in the same state. So, again, I mean, obviously right now everything is 0. So yeah, so the value of all the next states, whether I go up, down, left or right, is 0. Now, what is the transition probability for going the next state? In this entire setup of small world, It's a deterministic environment. So if I'm at a state 1, and if I take left, with 100% certainty I can say I'll go to the state 0, right? And so on and so forth. There is nothing probabilistic like, hey, I'm at state S and I take action A, then maybe I like there is a 50% chance I go to state S1 and 50% chance I go to state S2, right? There is no such stochasticity here. So the transition probability is just going to be 1 or 100%. I'll just fill that up, right? Uh, so yeah, and then I'll just let's just look at the formula. What is the formula? It is summation of certain something over the uh, all the action pairs, and summation of what exactly? The probability of A given S, right? What is the probability of going left if I am at state 1? It's 1 by 4, right? So 1 by 4 probability into the reward that I'm getting, which is minus 1. Gamma is 1. Let's just ignore it. And how many possible states are there? Just one. If I take left, I'll always go to zeroth state from first state. So there's just one. There is no summation required. It's just probability of one, probability transition probability of one multiplied by the value of the next state, right? So this is the formula I have written, and we are getting this for all the four action pairs, and this is nothing but the sum of all of that. So I hope you can see this Excel formula is nothing but the equation that we have written above. And of course, for in our case, things are a bit simpler because if I'm at a given state and if I take a single action, right, I'll always get to the same state, right? It's a deterministic environment, so things are simpler. This inner summation we don't require it, just the outer summation is there. So similarly, uh, right, let's now calculate for this state 2. So this v1, this is like iteration 1 for the state 2, right? Now from state 2 again, if you go left, the value is 0. If you go right, the value is 0. If you go down, the value is 0. If we go up, we remain at the same state, right? The value is still 0 because it's still in iteration 1. I have only updated, right? I haven't updated all the values yet. So let's just put these values of next states as zeros, right? And then um, same with this. This is cell 3. If I go to left, it's value 0. If I go to bottom, value 0. If I try to go to up or um, mm, right, I stay in the same state, right, and value is 0. So I'll just put the value 0 everywhere, and then we'll try to match it with the results from the book. Now finally the fifth state. Again, wherever we go, the value would still be 0. So yeah, this is again the sum of these terms in the probability into reward plus the probability into the next state value function. Now this is the matrix we are getting. We calculated for 5 cells and looks like it's a match. Now let's go to the second iteration. We'll just use this updated um, value from Sutton and Barto to start the second iteration, right? So again, this is second iteration. We have used the entire updated set of value function for each cell. And again, right, um, the probability is still, sorry, the policy is still uniform. It will be in the entire till we finish the policy evaluation, right? So it's always uniform, and whatever action we take, the reward is still -1. That's like a universal rule for this game. What will change, however, this time? Now, if I say go to, I'm at state one, then I go left, right? Then the value of left cell, which is terminal, is 0. However, for the other cells, it's -1, right? So let's just input that. I'm at state 1. If I go left, then it's 0. For rest of it, the value is -1, right? This is minus 1.75. Let's see if that matches the book. Yeah, so the book probably has an approximation till first digit, 1.7, and now we got minus 1.75. Now let's do it for the other cells. This is cell 2. Yeah, it should be actually the V2 of 2, but pardon my this notation. This should be, yeah, second iteration, cell 2, right. Uh, what would happen? I'm at this cell. If I go left, right, or bottom, I'll get -1 reward, right? And the values are -1. If I go try to go up, I'll remain in the same cell. And again, the same cell's value is -1. So I'll just input this, right? This is -2. Let's see if that's a match. Yes, it's -2. Uh, right. Now, if we're at state 3, we could go left or below, and we'll go get a reward of -1, and we'll go to states with value -1. And if we try to go up or right, again we'll remain in the same cell. And again, what is the value function for the same cell? -1 again, right? It's a -2. And let's correct this. This is not iteration 1, it's iteration 2 for the second cell. Similarly, this is iteration 2 for the mm, fifth cell, right? Yeah, so we're at cell 4. If we go up, then it would be 0. The value of the next cell would be 0. For rest of it, it's -1. Now, this fifth cell, what is the second iteration value? So here, whether regardless of we go up, left, right, or down, we'll always get the value of next cell would always be -1, and then obviously it can't go diagonally or some other cell. So it's again -1. So yeah, again, this result is nothing but sum of these probabilities. So we calculated for these 5 cells, and again, yeah, looks like it's a match. Now we'll do the third and final iteration of this policy evaluation. Here we'll do like just 6 steps just to be sure, right? Let's correct the notation. This is iteration 3 of this. Let me correct the rest. This is iteration 3 of state 3, iteration 3 of the cell 4, iteration 3, iteration 3. Yeah, now that the notation is corrected, this is pretty much same uh, process. I am here at cell 1. I could go left, right, below, or up, right? If I go up, I'll remain in the same cell. And if I go to left, what would happen? We'll go to a state which has a value of 0. And reward is always -1 in this entire game. It will never change. Now, what would happen if I go to the right? I'll go to this state, -2. If I go to down, if I go to up, I'll remain where I am, which is current state, right? What is current state here? Value of -1.7. And if I go down, -2, right? And this is -243. Let's see if that matches. Yes, -240, -24. Now let's do it for the this cell. What would happen if I go to left, -1.7? I go to right from this blue cell, which is, the current cell in consideration. If I go to right from -2, I again go to a cell with value -2. If I go down, again -2. What if I go up? I'll remain where I am, which is -2. And this is again, the formula is what this header says. Probability into the reward plus for each possible states after that action, what is the probability of each state and what is the value function of the state. But in our case, if I take an action, say, if I go left, right, there is just one state that's possible. So there is no inner summation, just to reiterate the previous concept because it's might be new to you. So anyway, let's do it for the other remaining cells. I'm at cell 3. What happens here? If I go left, -2, go right, -2. If I try to go up, I'll stay here, so -2. If I try to go right, there is nothing to the right, so I'll stay in -2. It's all -2 for this case. Now this V4, I like V third iteration for the state or cell 4. This is if I go up, right, what would happen? It would be 0. If I go to the left, I'll remain where I am, which is -1.7. If I try to go right, I'll go to from -1.7 and go to -2. And if I go down, again, I'll go to -2. Now let's go do it for the fifth state. If I go up or left, I'll get a -1.7. Up and left -1.7. If I go to right or down from the blue cell, I'll get a -2. Now for the last and sixth cell, third iteration. Here what happens, whether I take left, right, up, down, it's always -2. So for every possible state, the value function of that next step is -2. Right, let's see if the values match. -2.43, -2.43, -2.93, and this is 2.9, the approximation, -2.85. Okay, this is, let's just see if we did the fifth state correctly. Fifth state. Yeah, looks like it is correct. It's 2.85 -3. Let me just check what was the result in the previously that I solved earlier. Yeah, I was getting the same value. Anyway, so yeah, this is how this policy evaluation works. And again, we'll keep doing it till the optimal policy argmax doesn't change, right? And so that concludes the policy evaluation. And once you have the policy evaluation, you know what to do. You gotta find the greedily look for, hey, what is the best action? Like, I'm in this current state, I could take four actions. What is the best one? What will give me the maximum reward? That will give me a new policy, right? Now let's evaluate the new policy. That's the second loop, right? And once we evaluate it, then now let's improve it. Then again, let's after improving with a new policy, now let's evaluate that policy again. So this loop continues. So this is policy iteration. And mostly today, again, I just wanted to cover this grid world example because I couldn't find a good explanation anywhere online. So yeah, that's pretty much for today. We'll cover more topics from deep learning or reinforcement learning or NLP, etc. in the upcoming videos. Thank you so much. Stay tuned for further such videos. Thank you.